Hello, welcome, and a very Christmassy evening. And we're back at Let's Code MS-DOS, and this year's Christmas edition is again about Power Basic, the programming language, which we used the last years as well to code some Christmas spirity things. And this year we will code a snowflake, the Koch snowflake in particular, which is an iterated function system. That is, it's a recursive function that you apply to itself, and it will gradually produce these snowflake-shaped things. You start out with a so-called axiom, which is this triangle in this case, but there are other function systems that use different axioms. And then you recursively apply the Koch function to that, and it will subdivide and generate something which looks a bit like a snowflake. And we can do this by something called a Lindenmayer system or an L system. And it's actually pretty simple, such a system. Such a system has rules, and our Koch curve has only one rule. Namely this one here. If we encounter an f, we will produce something which is called f plus f minus minus f plus f. Okay, what does that mean? Basically, the f means draw a line forward into the direction we're facing. If you remember perhaps Logo and the turtle that you could use to draw things which could turn left or right and then draw forward, something similar happens here. The plus means turn left by 60 degrees, which are the angles that can be seen here in the corners of the snowflake. Let's scroll down again. And minus means turn right 60 degrees, so we will go forward for one curve segment, do the turn left by 60 degrees, draw forward, turn right by 120 degrees, draw forward, turn left again by 60 degrees and draw forward. And the f actually will of course produce another one of these rules. That means you will have a recursion here. So this f will expand to the whole term again. And at some point you have to stop that. Otherwise it will be an infinite curve, and you can actually zoom in infinitely into the curve. But on the computer we need to stop at some point, and we'll do 3, 4, 5 iterations, and that'll be it. And the constants here, plus minus, will be our turn function, and that's it. And if we want to have the snowflake, we will use this axiom: forward 120 degrees right, forward 120 degrees right, forward, which produces the triangle which we saw up here. So that is actually pretty simple, and as a starting point I used the code from Rosetta Code for the dragon curve, which is another L system and produces this interesting curve down here with a bit more rules, or let's say these are the rules, I think. But we will not look at this, but the nice thing here is there is a very simple QBasic implementation which I again use as a starting point, but I ripped apart some things. I kept the turn and forward thing, and we will re-implement a new function called Koch, and also the f operation which will apply the L system. So this was the starting thing. There's also a Koch curve implementation on Rosetta Code, but actually the QBasic one doesn't look very good. It's a lot of I would say spaghetti code, or at least it's way too complex. We can do this in a much simpler fashion. Rosetta Code itself is a pretty neat website. It has all sorts of algorithms and things in different programming languages. You can see here the dragon curve, for example. You can have it in C, Java, JavaScript, and very exotic languages as well. So basically there's an implementation for almost every programming language imaginable, which is fine. But we will stick to this representation of the Koch curve, and the nice thing is you can change the angles that you're making to generate different curves. So after I finish this, you can take the code and play around with the angles, or you can look up different L system rules and implement those. There are more complex Lindenmayer systems which allow you to draw trees and other organic structures. So yeah, it should be a starting point, and you can do this in BASIC pretty easily. So let's switch over to Power Basic. The source code will be on GitHub, and I will link to it in the video description. So right now you can just follow along. First of all, we need a variable that stores the angle of the turns we made. And this is the only difference to QBasic. This declaration here will be different in QBasic. It will, I think, be called dim shared angle as double. So QBasic probably needs it like this. Dim shared angle as double. There's a slight incompatibility between QBasic and Power Basic, but we stick with Power Basic because that's what we got. And you can download Power Basic, the free edition, on the web. Might also link to that in the video description, but you can also Google for it. Shouldn't be too hard to find. The freeware version will be just enough to do that, and you can let it run in DOSBox like I'm doing here. Don't need a real retro PC for that. Furthermore, we need a variable which I call col for color, but I can't use color because that's already taken in Power Basic, which will be an integer. It stores the current color of the snowflake. We will make different colors, 16 colors to be exact, because we are using the high-res VGA mode for that. And we will scale the snowflakes, make them smaller or bigger, and that will be a floating point double precision variable as well. Okay, first things first, we will switch to the graphics mode, and when we exit we will switch back to the text mode. Graphics mode is mode 12, which is 640 by 480. Okay, no numlock. 640 by 480, 16 colors. And this here is basically text mode, so we are nice when we quit. And we also want to have, every time we start this, a different outcome. And this will basically let us use this as a screensaver, for example, which is nice. And we will initialize the angle that we're using with 0. We probably can use some randomized angle here to rotate the snowflakes. We'll try that out later once we have that. And to make it a true screensaver, every 100 draws we will clear the screen. So we need to count how many draws we made. And if we run in an endless loop until someone presses the key, this we can do by using the instat function, which is 0 if there was no key pressed. So this whole thing here will run until someone presses the key. And let's also do the screen clearing here already. If the count exceeds 100, then we will clear the screen, CLS, and set the count, we're using lowercase here, count to 0, not that it matters, BASIC is not case sensitive. Else, we're just increasing the count by 1. So that's nice. Okay, that's good. What we need to implement? Well, we will have a function that I will call Koch, and it will need a few parameters. The first parameter will be how many pixels every leg of the curve will be, and I say 5 pixels so that it doesn't get too big. Then how many subdivisions, and I figured out 4 are pretty nice detail, not too much detail that it gets weird on the screen. We also need to pass it the scaling of the curve, so we need another variable called scale, which we defined up there, and also the color of the curve. There's some stuff missing, of course, now. Well, the things that are still missing is we need to have the initial point of the Koch curve, and since we're using the line command in BASIC, we can actually set the very first point that the lines will continue from. You don't always need to specify both ends of the line, you can just continue drawing lines and lines and lines, and it will just use the previous line's end as the next starting point. And we can set that with the pixel set command, and we'll set a pixel at some coordinate x and y with our color. Now we need to figure out what the coordinates will be and the scale. So the scale I'm just gonna set to minimum of 0.5, so making it half as large as it could be, plus some random number times 2. That can be arbitrary, but times 2 worked out in my experiments so that these curves or snowflakes fill at most roughly the screen, not more. The x-coordinate could simply be some random value times 640, which is the x resolution of the VGA screen, and the y-coordinate could be something RD times 480, which gives us coordinates between 0 and 640 and 0 and 480. That would be almost good enough, but then the curves or the snowflakes will always start somewhere inside of the screen. And I figured out we can shift them slightly by 160 roughly, which is a quarter of the screen, divided by the scale that we calculated to the left basically, and we can also shift it by 120 divided by the scale to the top, and then we will have a very equal distribution of snowflakes over the screen, even up here and to the left and to the top. That will look much better. You can play around with these values to limit where the snowflakes will appear, but this, in my case at least, worked pretty nicely to put them all over the screen. So what do we need to implement? We need to implement the Koch subroutine. We'll put that in between here. So we will have a subroutine called Koch, which will take a few parameters, 4 parameters. First will be called length, which is a double, could be an integer in pixels, but we can also specify fractions if we want. Doesn't matter much. We will use a double later anyway, because we will scale this by the amount we get in the scale. We will have an parameter called split, which is the same that was used in the implementation I showed you on Rosetta code, so I'm sticking with the parameter names here. Split will be an integer, and then scale again will be a double, naturally, and the color is of course an integer. Can range between 0 and 15. This is the end of the subroutine, and in between we are not doing much. We are doing the axiom, which was calling f, then doing a turn by 120 degrees, calling f, turn by 120 degrees, f again. Well, the subroutine f will also need the parameters that the Koch curve got, so we will just pass it length, split, however, -1, so when split reaches 0 we will stop, just draw the line and that's it. This will stop the recursion. If we don't do that, we will get into an infinite loop, which will be bad. The scale, of course, and the color. And we can actually copy all that. And that's it. So, next up, we have our axiom. Now we need to implement the f function, and since we're calling that here, well, doesn't matter much, we can put it up here. It will look, the signature will look exactly the same as the Koch function. Maybe not moving, copying will be better, yes. Alright. Does it still compile? Okay, it does not compile yet, because we need to also have the turn function, which takes degrees as a double. And we will leave that empty for now. And it will compile, but it won't do anything. So let's implement f first before we do the turn. The f function, well, first we need to deal with the recursion. If split equals 0, then we are at the end of our recursive procedure. Then we will simply do a forward movement, basically drawing a line, by length times scale. We could actually, in the end, we probably could factor scale and length out. That would probably be better, but I'm sticking with this now. You can optimize this at home. So let's do that with a certain color. And else we need to apply the recursive rule of the else system. And if we remember, that was something like doing f, then turning by minus 60 degrees, doing f again, turning by 120 degrees. Okay, should probably write that in different lines. Doing f, turning by minus 60, and then calling f again. And that's the whole thing. And of course, we need to copy the parameters again. We could make all that global, but that would be pretty nasty, so I'm not going to do that. That's basically already the implementation of the curve algorithm itself. What's still missing is the forward function and the turn function. So let's have a look at that. Forward needs some length, basically. Let's say that's a double, doesn't matter much, could be an integer, and of course the color that we're using. So that's the forward function. What are we gonna do here? We're gonna draw a line, and if you look up the command for that, if you want to do just a line from the last point, you write a dash, and then step, and then where to go, basically. And that is actually a tuple of x, y coordinates, and our x coordinate is the cosine of the current angle, which gives us the x coordinate, and we scale that by the length. And of course, if we want the y coordinate, we just take the sine of the angle. This is simple trigonometry. Basically, you should have had that in high school, I hope. Otherwise, you need to look it up on Wikipedia or something. But basically, you can say if you have an angle, you get the x coordinate on the graph by taking the cosine, and the y coordinate by taking the sine. Okay, furthermore, we need to pass the color, and that's our forward motion. That is the actual drawing. And then the turn is actually not that hard. Turn is basically just updating the angle, and that will do angle plus the degrees. But we need to have this in radians for the cosine sine function. So we will be doing a multiplication here by pi 314159.265 divided by 180. We probably could also do that in the forward motion, but we will do this less often in the turn, because the forward will be called much more often. But you can play with that, basically. Okay, this will update our angle, and this should already be enough. We have the main function, which will clear every 100 draws. compute some scale and x and y coordinates. We'll set the initial position for the Koch curve. We'll call the Koch function, and then it will draw the axiom, which is the triangle, and recursively do the f rule basically, which calls turn and forward. So let's see if that works. Nope, so some debugging is in order. And I found the reason. The color wasn't set. It was always 0, so we drew a lot of things, but they were all black. So the color can be computed by just doing R&D times 16, which will give us all the 16 colors, including black. And this is what it looks like, and it's actually pretty fast. So if we want to have it a bit slower, we can put a sleep 1 second here. Shorter delays are not possible, I think, but this will look like it. And every roughly 100 seconds it will clear the screen because it will get to full. And you can see here very nicely the whole snowflake curve, and you can play around with the production rules to produce different things, and you can see how it gets scaled up and down. And probably there are more improvisations that can be done, but I think this is already a pretty nice screensaver. And yeah, I will put up the link, as I said, to the GitHub repository, and yeah, you can check it out, you can play with it. Also don't make sure to download QBasic or PowerBasic to try this out. And I think these L systems are very nifty and they can produce a lot of cool stuff. So that's it for today. There will be maybe 1 or 2 more videos before the end is over. The year is over. The end is over. The year is over. But for Let's Code MS-DOS, I think that's it for this year. So have a very nice holiday and enjoy whatever's left of the year. Also, share, like, and subscribe as usual. If you want to support me via Patreon, that's always very welcome as well. And until next time, I hope to see you soon.